Chapter 3 is on atomic structure and electron configuration. In Chapter 3, Section 1, the atomic theory is discussed. The atomic theory tells us that all matter is composed of indivisible particles called atoms, and that certain characteristics are going to be shared by all chemical compounds. These observations led to three important laws that we're going to be discussing here shortly. The first atomic theory was proposed back in 400 BC by Greek philosophers, and they weren't tested until about 2,000 years later in 18th century Europe. The first law that I mentioned is called the law of definite proportions. And it tells us that any sample of a compound is always going to have the same composition by mass. So for instance, NaCl, sodium chloride. By mass, sodium chloride is always 39% sodium and 61% chlorine. It doesn't matter whether you get it from, my salt shaker at home, your salt shaker at home, it's still going to be 39% sodium, 61% chlorine. That is the law of definite proportions. The law of conservation of mass we've mentioned previously, which simply just means that we're not creating or destroying mass. So our product mass should be the same as our reactant mass if our experiment had relatively little error. And that's all this equation here is showing, that sulfur combined with oxygen gives us sulfur dioxide. If we were to actually weigh these out in the lab, we would get the amount of our products should be equivalent or nearly equivalent to our reactants. And the third law is the law of multiple proportions, which says that the mass ratio for combining one element with another are going to be expressed in small whole number ratios. So essentially, you're not going to be having 3/4 of an oxygen combining with 2/3 of a nitrogen. They're always going to be combining in whole numbers. Now, depending on how they have combined, they will give the compound completely different properties. For instance, all three of these combinations of nitrogen and oxygen are gases, but they are very different from one another. The first one, NO2, is actually a poisonous brown gas that's in smog. The second one here, nitrogen monoxide, is a colorless, odorless gas. And the third one, N2O, is actually an anesthetic. You've probably heard of laughing gas before. That's what that one is. So just the different proportions of those combinations of atoms, even though they're the same types of elements, they can still have very different properties based on how they're combined, and that's the law of multiple proportions. Dalton was one of the first people to come up with an atomic theory that was tested, and he produced his theory in 1803. And remember, a theory is something that is explaining a law and is supported by evidence. So this isn't just an idea, it's something that he's tested. So the first part to Dalton's theory is that matter is made of indivisible and indestructible atoms. The second part is that atoms of a given element are going to be identical in their properties. So any atom of oxygen is going to be similar to any other atom of oxygen. And then number 3 kind of goes with that. Atoms of different elements differ in their properties. So oxygen is going to have different properties than sulfur. Sulfur is going to have different properties than hydrogen. If they're different elements, they have different characteristics. And the last two parts of his theory is the atoms of different elements combine in simple whole number ratios to form compounds. So that's that law of multiple proportions. And the last part tells us that chemical reactions consist of the combination, separation, or rearrangement of atoms. And so those are all part of Dalton's atomic theory. As we went through those, you might have noticed that a couple of those principles are no longer valid. The first one mentioned that all matter is made of indivisible and indestructible particles. Well, since Dalton's time, we've since discovered subatomic particles, protons, neutrons, electrons. Those are all inside the atom, which Dalton didn't know at the time. And another part that he mentioned was that atoms combine with different types of elements to form compounds, but he didn't state anything about atoms combining with their own type. So for instance, the oxygen molecule O2, oxygen can combine with itself, not just other elements. So those have been just a couple revisions to Dalton's theory, but for the most part, it still is pretty accurate today. The atomic mass is one of the values that you'll find on the periodic table along with the atomic number. And the atomic number is simply how many protons an element has. The atomic mass is going to be the protons and the neutrons added together. In comparison, we don't really count the electrons because their mass is so tiny in comparison to the protons and neutrons that it's not going to contribute much. So we mainly just assume the atomic mass is protons and neutrons added together. The units are in atomic mass units, AMUs, or grams per mole. And the atomic mass is exactly 1/12 the mass of one carbon-12 atom. Carbon-12 was what was based, what the entire periodic table was based off of. It was an agreed scale back in 1962 at a joint conference of scientists that agreed that carbon-12 should be the standard. It was thought maybe to use hydrogen, but it is very, very small in comparison to everything else, and carbon just reacts with a lot of different things, so it made it a little bit better of a choice. But one AMU is 1/12 the mass of one carbon-12 atom. This here is just a little proof that you might want to use. It kind of just shows you why we use AMUs or grams per mole instead of kilograms or grams when dealing with atomic masses. The conversion factor up here, 1 AMU is equal to 1.66 times 10 to the negative 27th kilograms. Okay, that's a really, really tiny value. So this is just showing the mass of the copper atom. If you look at copper on the periodic table, you're going to see 63.546 AMUs or grams per mole. If we were to convert that into kilograms, you can see it comes out to 1.06 times 10 to the negative 25th kilograms. And that's just a much harder value to work with in calculations than 63. So that's one of the main reasons why we use the atomic mass units, just to help in simplification. A mole is the SI unit for amount of substance. And one value that's going to be important for you to remember is Avogadro's constant. We're going to be using this quite a bit throughout the semester. And Avogadro's constant is 6.02 times 10 to the 23rd particles per mole. So this might be atoms in a mole, could be molecules in a mole, formula units in a mole, some type of particles within that mole. And again, just a little reminder here that 1 AMU is equal to 1 gram per mole. When we start doing conversions back and forth between molecules and grams and moles, we will tend to use this grams per mole value for molar masses as opposed to the AMUs. And this is just one last calculation showing that AMUs and grams per mole are in fact equivalent, similar to a proof you might do in geometry class. Here's our conversion into kilograms from AMUs. Here's the conversion into grams, and then using Avogadro's constant we can see that the amount of AMUs is in fact the same value as gram per mole.